And welcome to the code space. In this video, we are going to learn about the Bellman food algorithm. In the last DSA class, we have seen a single source shortest path algorithm, like we have seen the Dikshitra algorithm, in which we can find the shortest distance between a particular node to all the other nodes. Here, we are again going to see an algorithm in which we find the shortest distance between a particular node to all the other nodes. And the time complexity of this algorithm is n into e, which means number of edges into number of nodes. So here we can clearly see that the time complexity of the Kshitra algorithm is much more lesser than the time complexity of Bellman 4. Then what is the point of using this algorithm? So I just want to say that the Bellman 4 algorithm can also be applicable even if the graph contains negative edges. For example, let's take a graph. Right. Here we can see that the graph contains the negative edge -1. Now, when you are considering the negative edges, there may be a possibility of formation of a negative cycle. If the graph contains negative cycles, then we can't find the shortest path between the nodes. It's actually the minus infinity, because let's consider a graph. Let's consider a graph with a negative edge causing a negative cycle. Like, first of all, let me clear you that if a negative edge is present in a graph and the graph is a undirected graph, then there must be a negative formation of a negative cycle, because a graph with undirected edges, even at least with one negative edge, it forms a negative cycle, because a person standing here can move to the graph, and the distance traveled by the person will decrease by 1, and if he again go back to the same edge, the distance will again decrease, which keeps on decreasing, which resembles that it is the minimum shortest path is the minus infinity, and we don't find the shortest path. So first of all, the clear point is that to use the Bellman-Ford algorithm, the graph must be a directed graph, as well as there should be no negative cycles. or we can use the same this algorithm to find whether the graph contains any negative cycles or not. And once you ensure that there is no negative cycle, then you can find the shortest path between particular node, source node, to all the other nodes. Here in this case, the shortest path between the node 0 to 1 is clear that it is 5, and the shortest path between node 0 to node 3 is obviously 7, and the shortest path between the node 0 to node 2 is 6, and the shortest path from the node 0 to node 4 is 7, and the shortest path, there is another possibility of reaching the node 3 from node 0 is to go through the edge 4, which is giving a minimum distance of 6. Here this minus 1 reduced the value 7 to 6. So this is going to be the shortest path than the previous path that we have traversed. So we're going to remove that, and the shortest path here becomes 6. So here in this manner, we are going to achieve the shortest path between the source node to all the other nodes by using the Bellman Ford algorithm. Like in this algorithm, we'll just relax all the edges for n minus 1 times. And while relaxing, we just take an edge, and let's say the current edge is from U to V. Then we'll update the distance. This distance array is the purpose of this distance array is as same as in the Dikshitra. Like in the distance of V, we're going to store the minimum distance from the source node to the node V. So the moment we got an edge which comes from any other edge to this edge V, and the value that is already present in the distance of V is more than the current distance between the current node U plus the weight, the edge from U to V. So we'll replace the distance of V with distance of U plus current weight W, weight of the edge. We're going to execute this statement for all the edges for n minus 1 times. Now, once you do this task, you get the minimum distance from the source node to all the other nodes. But if you want to check whether the graph contains any negative cycles or not, then you have to relax all the edges for one more time. If you check, if you check that there is any change in the values of the distance arrays, like you maintain another array and This time you'll store all the new values that are obtained by relaxing at nth time, and you'll compare this new array with the previous distance array. If there is any change in the array, it makes sure that there is a negative cycle in the array, which is decreasing the distance every time. And if you keep doing this, the distance will keep on decreasing and it reaches to minus infinity. So we'll stop here and convey that there are negative cycles in the graph. The time complexity of Bellman-Ford algorithm is number of nodes into number of edges, and the space complexity is order of number of nodes. For each node, we'll assign the minimum distance from the source node to that node. So let's implement the Bellman-Ford algorithm in the GFG compiler. Here, in this problem, he given a value v which stores the number of nodes and a vector of edges. And the best part about this algorithm is we don't need to maintain any adjacency list. We can directly relax all the edges by using the given edges. So first of all, let me create a distance array of size n. I mean size capital V here, all initialized with int max. Let me take a vector. Distance vector of size V with initial value as int max, and we know that the distance from the source node to source node is always 0, so I'm placing that here, and I'm going to relax all the edges for n minus 1 times. See here in this question, it is given that if the graph contains any negative cycles, you just return a minus 1. So first of all, let's obtain the distance for each node. Then we'll relax for the last time, and if it contains any negative cycles, we'll just simply return an empty array with minus 1. Let's traverse the edges array, auto edge, edges, and if distance of u, I mean edge of 0 is not equal to int max, which implies that we can reach from the source node to the current node u, and distance that is already stored in the array is greater than the distance to reach the node u plus the distance between the node u and v. that is edge of 2. Then we'll make the distance of edge of v to distance of u plus edge of. So here in this way we got the minimum distance by just relaxing all the edges for v minus 1 times. Let us check our code by returning the vector distance. If it is correct entirely, then we'll go for the case of negative edges. Let us compile our code. One, it's so it has successfully passed the first test case. Let's write the logic for the negative cycles. Here we're going to create another vector int negative with same size v and initial value with int max, and we'll again traverse the edge for lost time. But this time we're going to update the value of negative array. To be optimized, we don't need to maintain any further array. If the condition becomes true here, we can directly return -1 like as an array, as a vector. So I'm writing it in flower brackets, and that's all. Let's check the second case. So the problem in your code is the default value is told to set as 10 power 8, which we are using int max here. Let's change this and recompile our code. So you can see that it has successfully passed all the test cases. And I hope that you like this video. Thank you for watching.